Chapter 11 is on liquid, solids, and intermolecular forces. The way these videos work is I will talk through a bunch of slides. Often the first video has some introduction material to the chapter, so it's sometimes a little bit longer. And then I will work through problems to show examples. To start off this chapter, where we're talking about liquids and solids, we're going to talk about the different phases of water. So here's a table from your text that shows some properties of water in its different phases. So the densities of ice and liquid water are much higher than the density of steam, which makes sense because in the gas phase, molecules are spread out. The densities and molar volumes of both ice and liquid water are much closer to each other. Liquids and solids are more similar to each other than they are to gas. And one unique thing about water is that the density of ice is this is larger, it's smaller than the density of water. Ice is less dense than water, so it floats on top of it, which is not normal for a small molecule like that, but it is essential for life as we know it. If ice sunk, that would have huge consequences to the world's water systems. Think about ice sinking, that would kill all the fish. Now, how does a substance change phases? Between solid and liquid, it's pretty much just heating and cooling. Between liquid and gas, there can be pressure involved. So if you reduce the pressure, a liquid will go into the gas phase. If you increase pressure, you can cause a gas to condense and go into the liquid phase. Now, in order to understand why substances are solids, liquids, or gases at different temperatures, we have to talk about intermolecular attractions. So how strongly molecules are attracted to each other determines what state they are in. So if there are moderate to strong attractive forces in materials at room temperature, the material will be a solid or a liquid. And the stronger the attractive forces are, the higher the boiling point and the higher the melting point. Now, these attractive forces, why do they exist? The reason is because of attractive forces between opposite charges. So Coulomb's law here describes how charges are attracted to each other, and basically you get the closer they are, the more attraction there is, and the positive end of a polar molecule to the negative end of a polar molecule is going to be an attraction. Positive ion to negative ion is an attraction, and then we'll also talk about temporary charges in nonpolar molecules. Also with Coulomb's law, the larger the charge, the stronger the attraction, so that's what the Q's here are. And the longer the distance, the R, the weaker the attraction. Always keep in mind that these attractive forces are small if you compare them to bonding forces between atoms. So any intermolecular force here is going to be much smaller than the bonding of covalent or ionic bonds. So our trends in the strength of intermolecular attraction, we're going to be comparing different molecules to each other. The stronger the attractions, the more energy it will take to separate them. One good way to look at that is by looking at boiling point, because if you boil a liquid, it's going to require that you add enough energy to break all of those bonds, intermolecular attractions between the particles. But this is very important. When we boil things, we are not breaking the covalent bonds. Keep that in mind. But a quick way to look at what the attractions are, how strong they are, is the higher the normal boiling point of the liquid, the stronger the intermolecular forces. There are 3 types of attractive forces. The weakest one is dispersion forces or London dispersion forces. The middle one is dipole-dipole, and then hydrogen bonding is a stronger form of dipole-dipole bonds. And we're going to talk about each of these types of intermolecular forces. Dispersion forces are caused by fluctuations in the electronic distribution in atoms. So basically your electrons will temporarily move one way or the other way, and you get these temporary dipoles. Those attractive forces are called dispersion forces or London dispersion forces, and it's important, it's in red, all molecules and atoms have dispersion forces. As a temporary dipole is established in one molecule, it's going to induce a dipole in the surrounding molecules. So as one side of a molecule becomes slightly negative, that's going to essentially push the electrons away a little bit in the neighboring molecules, leaving a slightly positive end of the next molecule. Now, how big those induced dipoles or dispersion forces are is going to depend on several factors. The first is the polarizability of the electrons, which is dependent on the volume. So the bigger the molar mass, the more electrons there are, and the stronger the attractions are. So if you compare this set of molecules here to this set, these at the bottom have more electrons, and so they are going to have stronger dispersion forces. The other thing that makes a difference is the shape of the molecule, because if you have more surface-to-surface contact, you're going to have stronger attraction. So if we compare this to these spherical molecules, you can see that with the added surface area, you're going to get more forces between those two than between the two spheres in this picture. We can look at that by looking at the boiling points. Like I mentioned, boiling point's a good way to look at it, of the noble gases. So as we increase in molar mass, our boiling point also increases. Because there are more electrons, they're able to shift more, and so we get higher normal boiling points as we increase our molar mass. We can see the effect of shape by looking at the boiling points of N-alkanes. As we add more carbons on, our boiling point increases because of both added mass and the longer shape. If we just want to look at shape, we can look at N-pentane versus neopentane. So these have the same number of carbons, the same number of hydrogens. You can see the same molar masses, but the one that's more oblong in shape has a boiling point of 36.1 degrees Celsius, whereas the one that's more spherical has a boiling point of 9.5 degrees Celsius. So the longer and flatter the molecule, the higher the boiling point, the more intermolecular, or the stronger the dispersion forces. So let's practice. Choose the substance in each pair with the higher boiling point. So if we look at letter A, we are comparing CH4, which is essentially circular, to C4H10, which is more oblong. So of those two, C4H10 should be the higher boiling point. Then we have two isomers of C6H12, one that is kind of long and oblong essentially, and one that is in a ring shape. So the higher boiling point should be the one that is oblong. So there's the correct answers. Now, dipole-dipole attractions. We're moving on to our next category. Polar molecules have a permanent dipole. They also have dispersion forces, but in addition, there are dipole-dipole attractions. Because of that permanent dipole, it's going to add to the attractive forces because there's always a negative end and a positive end causing this dipole-dipole attraction. So the boiling points of polar molecules are going to be higher than the boiling points of nonpolar molecules. So we can compare formaldehyde and ethane, which have very similar molar masses, but formaldehyde has this oxygen is polar, there's your negative end and your positive end, whereas ethane is nonpolar, and you can see that our boiling point is higher in the polar molecule than it is in the nonpolar molecule. And as we increase our dipole moment, become more polar, our boiling point increases. The stronger the dipole, the higher the boiling point. So more practice, choose the substance with the higher boiling point. So let's look at polarity in these. These two molecules both have fluorines. Here our fluorines are pulling kind of in equal and opposite directions. And here our fluorines are attached to the same carbon, so we're going to have a stronger dipole in this second molecule. So that's going to be our higher boiling point. In letter B, again, we have polar molecules. Here our chlorines are pulling in equal and opposite directions. Here they're pulling in the same direction, so this is going to be our negative end, this is our positive end. So cis 1,2-dichloroethane is going to be our higher boiling point. Remember that the double bond, there's no rotation around it, so these are locked in those conformations. Our last category of molecule is hydrogen bonding. When we have a very electronegative atom bonded to hydrogen, it's going to pull the bonding electrons towards it. So the ones you want to look out for are an OH, an NH, and occasionally an FH bond. And because hydrogen doesn't have any other electrons, when that electron is pulled away, the nucleus becomes deshielded, exposing the proton. And so that's going to act as a strong center of positive charge, attracting everything around it. So when you see an OH, an NH, or an FH, you should be on the lookout for hydrogen bonding, which is basically just a strong version of dipole-dipole. So in water here, it's kind of the classic example of hydrogen bonding. The more electronegative oxygen is pulling the electrons away from our hydrogens there, leaving that one proton deshielded, and so we get these stronger positive areas here, which are then attracted to the negative end of the oxygen, giving us hydrogen bonding. Hydrogen bonding has a significant effect on boiling points. If we compare ethanol, which is capable of hydrogen bonding, see the oxygen with the hydrogen bound to it, to dimethyl ether, which has the same elements, but the oxygen is in the middle and is not capable of hydrogen bonding because there's no hydrogen bound to it. You can see the difference in boiling point from negative 22 degrees Celsius to 78 degrees Celsius when hydrogen bonds are present. Hydrogen bonds are the strongest intermolecular forces, and but remember that they are not as strong as covalent or ionic bonds. So another practice question, choose the substance in each pair that is a liquid at room temperature with the knowledge that the other one is a gas. So letter A, we're comparing something with an OH group to something with two fluorines on it. The OH is capable of hydrogen bonding, so that's going to be our liquid at room temperature. And then over here, the one on the left here has an oxygen in the middle, but there's no hydrogen. And the one on the right has an NH2 group, and remember NH is one of the ones you have to look out for. So the one on the right here is capable of hydrogen bonding, and so it is a liquid at room temperature. Hydrogen bonding is important not only in chemistry, but also in biology. So here's an example of DNA. The way DNA works is it is a double helix structure that is held together by hydrogen bonds. And the way, so it base pairs thymine with adenine, cytosine with guanine, and the way that DNA is synthesized is the hydrogen bond pattern is recognized by the enzyme doing the replication process, and so the correct opposite base pair can be put into place. As you can see here, there's a T here and the A is coming into base pair. So that is one way that DNA is, it's how DNA is copied, and it's a mechanism so that mistakes happen infrequently. There's more to it than that, but so hydrogen bonds, important in chemistry, important in biology. Okay, now we're moving on to understanding some properties of liquids now that we understand these intermolecular forces. The first property we're going to look at is miscibility, which is the ability to mix without separating into two states. And the rule for miscibility is like dissolves like. So if one of the substances can hydrogen bond, say water, and the other one can't, so water has London dispersion forces, dipole-dipole, and hydrogen bonding. C5H12 pentane only has London dispersion forces. Those are not alike, so they do not dissolve in each other. So if you want to predict if two liquids will dissolve in each other, you have to look at the intermolecular forces. If they are like each other, they will be miscible. Another example of this is ion-dipole attraction. We've talked back in Chem 103 about salts dissolving in water, and the strength of the interaction between the ions in the salt and the water is called ion-dipole attraction, and it helps determine the solubility of ionic compounds in water. So the more attraction there is between the dipoles in water and whatever charge is on the ions, the more soluble the compound is. So more practice. Choose the substance in each pair that is more soluble in water. So letter A, again, we want to look at the intermolecular forces. So everything has London dispersion forces. This molecule is polar, so it has dipole-dipole, and it has the OH group, so it can hydrogen bond. This one over on the right, everything has London dispersion forces. It has a fluorine here, or two fluorines. So it is polar, so it has some dipole-dipole, but it can't hydrogen bond. So the one that is most like water is going to be the one on the left. Then if we go down to the bottom, this chain of carbons only has London dispersion forces. Our one on the right, of course, has London dispersion forces, but it also has a chlorine, so it's polar. So it has dipole-dipole, and that's going to be more like water than the one with just London dispersion forces, and so the one on the right is the correct answer there. So here's just a summary table. showing the different kinds of intermolecular forces, from dispersion to dipole-dipole to hydrogen bonding, and then ion-dipole, where you're mixing ionic compounds and polar compounds.